Hi, good morning all. Welcome back to the lecture video sessions on the performance of transmission lines. To reiterate the previous video sessions, what we have discussed about the different type of transmission lines, we discussed the short transmission line and the effect of the efficiency, load power factor, and then the regulation, which is very important factor, which is going to decide the efficiency of a particular transmission lines. And we have also discussed about the performance of the short transmission line, and we understood that short transmission lines are shorter in length, below around 80 kilometers length, and then around below 50 to 80 kilometers length, and then it carries the voltage up to 20 kilovolts, and hence the capacitance effect is almost ignored compared to the other two parameters, resistance and the inductance. So we have also drawn the equivalent circuit, and then we have analyzed the phasor diagram, and we have derived the formula for the efficiency as well as the regulation. And with respect to the regulation, we understood that what is the receiving end voltage and what is the effect of the receiving end power factor. And also we have come to a very important conclusion that AC distribution has got a major impact because of the load and power factor. So it is always advisable for the consumers to maintain a better power factor so that the power efficiency will be maintained, and then the transmission efficiency can also be kept at the minimum losses. So here, going with the other type of transmission line, which is called as a medium transmission line, wherein the length of the transmission line is between 50 to 100 kilometer, and it carries more than 20 kilovolts. These type of transmission lines operates at more than 20 kV. In such cases where the length is more than 50 kilometer and then the carrying capacity of the transmission line is more than 20 kV, the effect of the capacitance comes into the picture. So we need to account this capacitance which exists between the two lines, considering the air between the lines as the dielectric medium. Here we consider three different type of parameters that exist in the transmission line. They are resistance, inductance, and the capacitance. So when we do the performance analysis of medium transmission line, we need to consider the capacitance effect for the better accuracy, and we need to understand that the effect of the capacitance is very much visible for medium transmission line and long transmission line. So the capacitance here, it is considered as uniformly distributed, and it is not considered as a lumped parameter as like in a short transmission line, that resistance and then the inductances. So here it is considered to be uniformly distributed along the length of the transmission line. For the simplicity in the calculations, we can consider the line capacitance to be lumped on some part of the line, that is maybe at the receiving end or between the two lines, that is at the center, or distributed all along both the sides of the transmission line. So we can conduct the performance analysis of the medium transmission line using the three different methods. The first one is the end condenser method, second one is nominal T method, third one is nominal pi method. Let's consider one by one, and then we will be able to analyze all of them with the help of the phasor diagram, and to see that what is the performance what the performance analysis of the medium transmission line says. Let's take the example that is for the end condenser method. Let's take up this particular method to see how the performance of the line is. In the end condenser method, here we can see that the resistance and then the inductive reactance are connected in series, and then it is considered to be the lumped parameter, that is R plus JXL. It will be in the vector form, and there is a load that is connected at the receiving end, and then the voltage across the receiving end is VR. And since it is the end condenser method, we are going to consider the capacitance of the transmission line that is existing due to the length of the line at the end of the transmission line, that is near the receiving end. So here we consider the capacitance as a C, and there is a current that is flowing through it, which is IC, and IS is the current from the supply end, and Vs is the supply voltage, that is the supply end voltage. And here is the line, and then for the analysis purpose we are going to consider the single phase line. So one line and then one neutral constitutes a single phase. Now let's consider the phasor diagram that is drawn on the basis of the equivalent diagram. Here resistance says that the current and then the voltage are in phase. Inductive So R says that the resistance says that the current and the voltage are in phase, that is Is and the voltage are in phase, and inductive reactance says that there is a phase difference between the current and then the voltage, and it has got a lagging power factor, and the capacitance says that there is a phase shift between current and the voltage, and it goes with the leading power factor. Let's see the phasor diagram where we are taking the VR as the receiving end voltage as the reference vector, and with respect to this VR, current IR is at a phase difference, that is at a phase angle of phi r, and let's consider the angle between the Vs and the VR, that is the supply voltage, and then the receiving end voltage is a small angle, that is del, and phi s is the phase difference, the phase angle between the Vs and Is, and phi r is the angle between VR and IR. The vector sum of Is and IR, where IR and Is gives us the total current, that is IC, that is the current that is flowing through the capacitance. So IC is nothing but the vector sum of Is and IR. IR is the current that is flowing through the load. So the drop ISR is in phase with IR, and then IS, and so the drop ISR is in phase with Is, and then it can be plotted like this. At an angle of 90 degrees there is a drop Is into XL due to the inductive reactance. The vector sum of ISR and ISR and then ISXL gives us the line that is between the Vs and then the total voltage VR and then the Vs total voltage. So here in this method we consider the line capacitance is lumped or concentrated at the receiving end or near the load. So this method estimates, and then it calculates that it is a overestimate, it overestimates the effect of the capacitance. Normally capacitance is used to improve the power factor, so here we overestimate the effect of the capacitance so that the load end power factor will be almost equal to unity. So here we expect the capacitance to keep the power factor of the receiving end at the highest level, that is at the optimum level. So figure 1 shows the single phase line. As I already said, the VR is the receiving end voltage, Vs is the sending end voltage, XL is the inductive reactance per phase, IR is the load current per phase, and C is the capacitance per phase, and cos phi r is the receiving end power factor. So here VR is the reference vector from the phasor diagram. VR is nothing but equal to VR at an angle 0 degrees, that can be written as VR plus J0. Keep this equation as the 1. And the load current IR is lagging behind VR by an angle phi r. IR, from this we can write it as IR is equal to IR into cos phi r minus J sin phi r. Keep this equation as 2. Now capacitive current IC is the vector sum of Is and IR, which can be written as VR divided by minus JXC. And since it is VR divided by minus JXC, XC can be written as 1 over J by 2 pi FC, that is VR divided by 1 over J 2 pi FC. Since J goes to the denominator, the minus sign will go off. So it can be written as J into 2 pi FC into VR. So 2 pi F can be written as omega, J into omega into C into VR vector. That is, keep this equation as 3. From the phasor diagram, the sending end current is a sum of IR and IC. As I already said, Is is the vector sum of IR and IC. Now we can write this IR as IR into cos phi r minus J sin phi r, plus IC is nothing but J omega C VR. Then if we simplify this equation, we get it as Is is equal to IR into cos phi r minus IR into IR into sin phi r plus omega C into VR. Take the J out. So we can get it as plus J into minus IR sin phi r plus J omega C into VR. Keep this as equation 5. Now after knowing the currents Is and IR, that is Is and IR here, we know that IC and then Is and IR. So now after knowing all these currents, we can calculate the voltage drop in each phase. Voltage drop per phase is nothing but equal to Is into Z, that is Z is the impedance of the line, Is vector into Z vector minus Is into R plus JXL. If we go back to the figure 1, we can see this, like in this particular diagram, Is into R plus JXL here and IC into VC, and here we can consider the total near the load end. So Is is equal to IR into cos phi r plus J into minus IR sin phi r plus J is common between these two. So omega C VR, keep this as equation 5. Voltage drop per phase is equal to Is into Z minus Is into R plus JXL, referring to the figure 1. Keep this as equation 6. Now sending end voltage Vs is nothing but equal to VR plus Z into Is. Z is the impedance of the line. Z is nothing but equal to R plus JXL. So VR plus Is into Z is nothing but R plus JXL. So keep this as equation 7. Now voltage regulation is given as percentage voltage regulation is equal to Vs minus Vr divided by Vr. Vr is nothing but the receiving end voltage. So Vs minus Vr divided by Vr into 100. So similarly, efficiency of a transmission line is nothing but percentage transmission line efficiency is equal to percentage transmission efficiency, that is equal to power delivered per phase divided by power sent per phase plus losses. This we have done in the last previous video session, and we understood that power delivered per phase, that is nothing but equal to VR into IR into cos phi r divided by power sent per phase is nothing but Vs into Is into cos phi s plus losses is nothing but equal to Is square into R. So equation 8. Now limitations or disadvantages of this method of performance analysis using the end condenser method are: this method assumes that the line capacitance is lumped near the receiving end, but in actual practice it is distributed over the line. It is only the assumption that we are making to calculate the effect of the capacitance in this performance analysis. So we have considered that the total line capacitance is lumped at the receiving end. So however, this is hence a considerate error of around 10% can be considered after doing the performance analysis. This 10% is expected to occur in the calculations that going ahead, and effect of the line capacitances are overestimated. So we estimate that due to the presence of the line capacitance, the power factor is always at the optimum. So this is overestimated, may not be in actual. So, but advantages are also there. This method is very simple to have the performance analysis of the medium transmission line. Easy to calculate the sending end power factor and then the sending end current and the percentage efficiency, percentage transmission efficiency, as well as the voltage regulation. Let's consider one small example to this. This is a tutorial problem which is a very important one and which has appeared many a times in the university examination. Let's consider this. Medium single phase transmission line, 100 kilometer long. Here you can observe that it is more than 50 kilometers along the following 100 kilometer long, has the following constants. In case in the problem, if it is not mentioned that it is a medium single phase transmission line, with the help of this length of the line, we can assume that it could be a medium transmission line. So the resistance per kilometer per phase is given as 0.15 ohms. Inductive reactance XL is given 0.377 ohms. Capacitive reactance XC per kilometer per phase is given 31.87 ohms. And receiving end line voltage VR is given as 132 kV. And assuming that the total capacitance of the line is localized at the receiving end. So this says that at the receiving end, the moment it says that it is at the receiving end, we can assume that it is an end condenser method. So now apply the end condenser method and then determine sending end current Is, line value of the sending end voltage, that is Vs, line value of the line Vs, regulation Vs minus Vr divided by Vr into 100, and sending end power factor cos phi s. Now the line is delivering 72 megawatt, that is the capacity of this of this particular line at 0.8 power factor lagging. Let's write the diagram as the medium transmission line, and then the problem says that it is an end condenser method. Let's write the single line diagram, that is single phase diagram, with the lumped parameters R and L and capacitance near the receiving end, and VR voltage at the receiving end, IC current flowing through the capacitance, IR that is the current flowing through the load, IS sending end current, and VS is the sending end voltage. Here in the problem it is given as total resistance per kilometer per phase, that is 0.15. Since it is 100 kilometer long, calculate 0.15 into 100, that is 15 ohms. Total inductive reactance 0.377 into 100, that is 37.7. Total inductive reactance 0.377 multiplied by 100, 37.7. Total capacitive reactance Xc 31.87 multiplied by 100, 318.7. That is 31.87, 318.7. So now VR line is nothing but line voltage that is given at the receiving end 132 kV. Now capacitive current can be calculated as IC is equal to IC into j omega C into VR. So now VR divided by omega C is nothing but equal to 1 over omega C, that is XC, j into VR divided by XC. Now we know the value of VR, that is 132 into 10 to the power 3 divided by 3187 into j. So now IC is equal to j into 41.41 amperes. Now receiving end power can be calculated because we know about VR and then IR into cos phi r. So IR is nothing but equal to receiving end power divided by VR into cos phi r. Receiving end power is given as 72 megawatt, that is 72 into 10 to the power 6 divided by IR is, that is VR is equal to 132 into 10 to the power 3 into cos phi r is given as 0.8. Calculate, we will get 681.81 amperes. Now, after knowing this, we need to know that at what angle this is existing. So, IR is equal to 681.81 at an angle of minus cos inverse of 0.8. So, cos phi is given as 0.8, cos phi r is given as 0.8. So, now angle is minus cos inverse of 0.8. So, it is at an angle minus 36.86 amperes. Now IS is nothing but the vector sum of IR and IC, that is IR plus IC. Now we can add this 681.81 at an angle minus 36.86 plus J 41.41, simplify and do the addition summation, we will get 657.79 at an angle minus 33.97, approximate it to 34 degrees. Now sending end voltage Vs is nothing but equal to VR plus Is into Z. Now Z value is known, IR is known and VR is known. Calculate, we will get 154.778 kilovolts, that is sending end voltage Vs is equal to 154.778. So from VR, Is is at an angle 34 degrees and Vs is at an angle 5.77 degrees. Now 5.77 degrees, so sending end power factor is nothing but equal to cos of, if you refer the phasor diagram, we can understand that it is at 34 degrees plus 5.77 degrees. That is sending end power factor is nothing but equal to cos of summation phi r plus phi s, that is 39.57 degree. If we convert, it will be 0.77 lag. Now percentage regulation is equal to Vs minus Vr divided by Vr multiplied by 100. That is 154.77 minus 132 divided by 132 into 100. So percentage regulation is 17.25. Roughly around 18% to close to 18 to 17.5 to 18% we will normally get for a regulation, percentage regulation. So now after getting the angles, we can write with reference to this reference phasor is VR. At an angle of 5.57 degrees, we have the Vs and at an angle of 34 degrees, we have got the sending end current, that is Is. So problems are pretty simple and then it will be very easy to calculate and then see that what exactly the values are. Now moving ahead, we have got another way of doing the performance analysis of medium transmission line. The most important one, that is the nominal T method. In this nominal T method, figure 1 shows the equivalent diagram of the nominal T method, where we are considering the capacitance to exist or to concentrate at the center of the transmission line, where the transmission line is divided into two halves, that is R by 2 and XL divided by 2, and the capacitance of the transmission line is lumped in or concentrated at the center of the transmission line. So let VR is the voltage across the load and then XL divided by 2 and RL divided by 2 on either side of the capacitance, and current IC flows through the capacitance, and then the let us consider the V1 is the voltage across the capacitance C, Is is the current, that is the sending end current, and Vs is the sending end voltage. So as I said, the capacitance is assumed to be concentrated at the midpoint of the line. So the values of the resistance and the reactance is halved into either side, that is divided by 2. Now it is always preferable